Cool. Oh. Should I be cool here? No. Okay. Paper 236. Sadiko Bari, is he presenting? Or Labuni Afrus? Okay. Paper 116. Ashame Akbar. Okay. Paper 87. Your which one? Muhammad Sadiul Alam. Which you remember? Sorry?
Paper 87.
Oh, yeah, okay. Yeah. So the last one. Okay. So are we ready? Yes. Can we have the first presenter, Tahsinul Haq? We have 2 hours. If we can have 15 minutes per paper, that we can make it in 2 hours. Yeah, 1, 2.
Good afternoon. Thank you for giving me the opportunity to present the paper Effect of Fish Wedge on the Hydrodynamic Characteristics of a Marine Radar by me, Tahsinul Haq Tasif, and Professor Dr. Muhammad Mashood Karim, Department of Naval Architecture and Marine Engineering, Bangladesh University of Engineering and Technology. The objective of this research work is to investigate the effect of fish wedge in the section of different length on the hydrodynamic characteristics of marine radar with an NACA 0012 airfoil section, to investigate the effect of fish wedge section with a length 5% of the chord length of NACA 0012 airfoil section when using as a flap, and to compare the hydrodynamic characteristics of fish wedge of different lengths with the fish wedge used as a flap. The motivation of this research work: the harbor tugboats face tremendous difficulty when maneuvering the very large vessels in comparatively narrow channels. The tugboats also need to decrease its tactical diameter to change its course in a short area near port. Because of these reasons, this research work focuses on the application of fish wedge section to increase the lift force of the radar section, which creates easy turning of the vessel and solves the problem. The methodology: fish wedge section. In this case of study, fish wedge section with different lengths ranging from 5% to 0.5% of the chord length is studied. And in every case of a study, the tail wedge section has a constant height of the 2.5% of the chord length. In every case of study, the flow is generated ranging from 0 degree to 20 degrees angle of attack, and the generated lift and the drag coefficient is obtained. After this, the fish wedge sections having the length 5% of the chord length is used as a flap, and it is positioned from 0 degree to 10 degree, and again the flow is generated ranging from 0 degree to 20 degree angle of attack, and the generated lift coefficient is obtained. Computational fluid dynamics, ANSYS Fluent. In this case of study, I have used ANSYS Fluent as a simulation with the simulation code. It is a finite volume based the CFD code. I have used the ANSYS the workbench to generate the mesh, and I have used ANSYS Fluent to generate the flow. Computational domain. Here we can see the full computational domain of the fish wedge section. The leading edge of the airfoil section is positioned 1 meter from the inlet, and the fish wedge section is positioned 2 meter from the outlet. The grid is, as I have already said, is generated by ANSYS workbench. In the left hand side figure, we can see the full view of the computational domain and the grid, generated grid. And in the right hand side figure, we can see the detailed view of the domain. Here I have used fine mesh near the rudder wall to capture the turbulent flow near the rudder wall, and in the rest of the domain there is the coarse meshes. Now validation, I have generated flows ranging from 0 degree to 10 degree angle of attack, and the generated lift the force is validated with the experiment done by Abbott and von Duyanoff. This validation was for NACA 0012 airfoil section. After this, fish wedge sections with different lengths has been added at the trailing edge of the NACA 0012 airfoil section, and from this the figures we can see that if the length of the fish wedge section is decreased, and then the lift coefficient increases, and it increases drastically if the fish wedge section is decreased from 2 degree to 2% of the chord length to the 1% of the chord length, and it actually doesn't much changes if we decrease the length of the fish wedge section less than 1% of the chord length. And again, the lift coefficient doesn't changes much if we if we decrease the length of the fish wedge section less than 3% of the chord length. Here I have used two different turbulence model to calculate the lift coefficient. Here we can see the drag coefficient of different fish wedge sections. This drag coefficient is almost same for different fish wedge sections, having 2.5% fish wedge section height, and it is almost similar with the NACA 0012 the airfoil section experimental result. Here is the comparison of lift coefficient versus drag coefficient between NACA 0012 airfoil section and different fish wedge sections. Now, if the fish wedge sections of having 5% in the length of the chord length is used as a flap, and it is positioned 0 degree to 10 degree, then the lift coefficient increases gradually, and the maximum lift coefficient is found at the 18 degree angle of attack. Now comparison is made between fish wedge sections and fish wedge section used as a flap. Here we can see that if the fish wedge sections of having 5% length of the chord length is used as a flap, and it is positioned at a 10 degree, and the flap is positioned at 10 degree, then the generated lift coefficient will be the same as the lift coefficient generated by 1% of the chord length of the fish wedge section length. Now conclusion. These fish wedge sections with constant height of 2.5% of the chord length can increase the maximum lift coefficient up to 15% of the lift coefficient generated by the NACA 0012 airfoil section. Lift coefficient increases drastically from a wedge section of length 2% to 1% of the chord length. Drag coefficient doesn't change significantly with the length, and if the fish wedge section of length 5% of the chord length can be used as a flap, then it can at the position of the 10 degree, the flap can produce the same maximum lift coefficient generated by the wedge section of length 0.5%. Now recommendations. In the fish wedge sections with the length 0.5% of the chord length can be used as the rudder section to increase the maneuverability of the tugboats working at port or the narrow channels. The fish wedge sections with the length 5% of the chord length can be used as a flap to get variable lift coefficients, and the fish wedge section with the length 5% of the chord length is used as a flap is more suitable for use in the tugboats, as it could produce the same maximum lift coefficient and also variable lift coefficient at different angles of attack. These are the references of my research work, and thank you. If you have any question, please feel free to ask.
Okay. So can we have a question from the floor? This is a very interesting subject.
Thank you, sir.
Yes. Okay, I'll start first. Why don't you increase the area of the rudder instead of putting the...
Sir, there is a plan to increase the area. In every case of study, I have used 1 meter of the chord length, with including the fish wedge section. But there is a plan to increase the rudder section and then estimate the lift the coefficient in future.
I'm also trying to understand how this, you call it what, fish wedge section, how does it increase the lift of the rudder?
Sir,
okay, I can see the plot, but I don't see if you have pressure distribution. I can.
When this fish wedge section changes the direction of the flow at the trailing edge of the rudder, and this produces the much more the lift forces than the normal rudder section.
Oh, so you have a rudder like this and it open up.
Yes, sir.
Oh, I see.
Sir, like this, sir.
I see. Because you only show 2D,
This
you don't see the 3D. So.
No, sir. This is done in 2D.
Okay. So any question? So anyway, so we'll give you a round of applause for your presentation. Thank you very much.
Thank you, sir.
The next paper is Alimuddin and Islam. The paper is prediction of motion of a semi-submersible.
Assalamu alaikum warahmatullahi wabarakatuh. My name is Muhammad Alimuddin and I am going to present my paper, Prediction of Motion of a Semi-Submersible, on behalf of my professor and me. And my professor name was Muhammad Islam, a professor in the Department of Naval Architecture and Engineering. And so, and the outline of my presentation is the background, motivation of the research, and what is the objectives, and the methodology, that method I used, and mathematical model, and comparison of results, and finally some conclusion and recommendations, how we can improve the further research. And actually, semi-submersible, it is actually one kind of offshore structures. And you know that offshore structures platforms are used for various purposes, for research purpose, for extracting oil and gas from the ocean. And it's very, and the first offshore platform was installed in 1947. That is, and today there are around 6,500 offshore structure platforms in the world. And at first, what is semi-submersible? And that is one kind of offshore structure, and it has more stability than the surface ship. And for extracting oil and gas, you need more stable structures. If you use surface ship, it faces more waves and motions are very high. So you cannot use surface ship for extracting oil and gas purpose, for exploring oil and gas. And the motivation of the research. And actually, the numerous analysis that was done in previous was not so much. And most of the research work was based on the simple cylinder or box, etc., etc. And so I tried to use semi-submersible. Taking more complex structure for my analysis. And another another purpose is that Bangladesh has recently achieved Bay of Bengal more than 20,000 square kilometers and including exclusive economic zone. And generally, oils and gas are found in deep sea region. And so far, there is no alternative offshore structures. If you want to explore oil and gas from the ocean, that means in the Bay of Bengal. And my objective was the competition of motions of this semi-submersible using Hydrostar, and you know that Hydrostar is a commercial software, and that's competition software. And finally, comparison between published experiment result and a Hydrostar analysis. And published experiment result, I didn't know about the experiment result due to the lack of a tank here. And the methodology. And actually, the developed mathematical model was used based on the linear wave theory and 3D source distribution method to technique the motion of a semi-submersible. Actually, it has been based on the velocity potential of the floating structures. And for implementing this method, you have to discretize the whole surface area into number of panels. Number of panels, and finally I have compared this my motion results of the motions with the published experimental result. And there are some assumptions in my analysis. Actually, the fluid is assumed to be ideal irrotational. And fluid is homogeneous, and absolute viscosity is not included in Hydrostar analysis, but in real form viscosity is absolutely included. And the regular in real case, waves are not regular, but in my analysis, I have considered the wave was regular. And there are some governing equations. Governing equations I have discussed, and at first I have to use the velocity potential, and finding a potential, you have to use the Green function, and you know that Green function is a complex equation, and you have to use some boundary condition for finding added mass coefficient, damping coefficient, etc. For finally found the equation of the motion. And equation of motion, there are some inertia force, damping force, resisting force, and exciting force. And if you found that, then you will get the equation of motion, and finally the equation of motion. And actually, this is the particulars of semi-submersible. It is also called semi. And there is some particulars, and it was a 4-column based semi-submersible, and also 2 pontoon, and the length of the pontoon was mentioned here, and then this is the comparison between experimental and Hydrostar output. And at first there's heave motion. Heave motions, that means it's the vertical motions of the structure, vertical motion structure, and you see that the heave motions, the motion is very high at low frequency, and there is some discrepancy between the heave motion experimental result and the Hydrostar result, and there's some reason why this is the result is like that. And in the pitch motion, you found that there is it's a lot of discrepancy, and actually in the experimental result, the author who has done this experimental result, he said that actually viscosity was considered. There was a limitation in the turning tank. He could not use regular waves, and he could not regular waves. And so that he was also in doubt that their experiment results may have some errors. But I didn't do experiment results due to, I've said, that lack of turning tank. And this is a surge motion. And the surge motion, that is, the trend is same, but not much my result and the experimental result. And here also the same reason. And then the motions are different heading angles, heading angles. And then you see that heave motions, if you change the heading angles, 90, 135, 180, it is not so much different. This is a vertical motion. And if you change the angle of heading angle, then I found a similar result from the Hydrostar, and there its experimental result is not available. And then pitch motion. The pitch motion that is very high when the heading angle is 180. Then when it comes at for the ship, then it's more pitch, it faces more pitch. And the surge motion. And surge motion is high for head C condition. And the one condition is head C and beam C. Head C means its angle of heading is 180 and beam C its angle of heading is 90 degree. And motion is high for head C condition and low for beam C condition. And the shear motion. And the shear motion is also high for, in this is reverse condition, motion is very high for beam C condition and low for head C condition. And I found this result from the analyzing hydrostar, that I didn't discuss here, total procedure actually. And the roll motion, and this is the most important thing in the ship analysis, the roll motion. When ship rolls, the motion is also high for beam C condition. That means the ship speed, ship direction, and the direction is 90 degree. Then it gets a more roll, and so the result is compatible. And yaw motion, and that is also the heading angle for 90. I can find out this result for more angles, but I've shown here only for 3 heading angles. And conclusion, and the experiment results are, I said, experiment results are calculated considering mooring arrangement, but in hydrostar, I didn't consider any mooring arrangement. And so then we have discrepancy in the results I have shown. And viscosity effect was also not considered. And in real life, there is absolute viscosity effect. And when he has done, the author, he has done experiment, the viscosity was there. But in computational analysis, hydrostar doesn't work with viscosity. And so the results may vary. And also the regular waves are considered, but waves are considered, but actually in real life, waves are not regular. So further analysis can be done considering irregular waves. And some future recommendation, and the more realistic for finding more realistic results, analysis for irregular waves is appreciable. Then I hope we'll get the more realistic result. And similar procedure can be applied for any other semi-submersible, any other offshore structure. And the question, that question may arise, that why I have used these experimental results. And my intention was that if I find close results, very close results, or if I find any discrepancy and very close, if I find close result, then in future I can use this similar method for those structures whose experimental results are still unknown. That was my actual intention. And thank you very much.
Okay, thank you very much.
If you have any question, then I'll try my best to give answer.
Any question? Any people doing research on semi-submersible?
Yes, sir.
I did research on semi-submersible.
Yes,
I think the most difficult thing about semi-submersible experiment is that on the surging side,
yes,
with the mooring.
yes, sir.
Do you know the natural frequency of mooring? The natural frequency for mooring?
No, sir. Actually, I don't know about mooring analysis.
For full scale about 100 second
Yes.
period. So very hard to do this in the lab to generate
Yes, sir.
wave for what for that frequency.
Yes, sir. I said that I couldn't use if there is time tank is unavailable here, so I couldn't do the experiment once again. I think that further analysis can be done using various type of structures, the same structures. If then result will be compared, then I will get more realistic result that what was happened in just those time tank.
And another way you can check like heaving and pitching by using Morrison's equation.
Yes, sir. Morrison.
Your cylinder and pontoon. We can check whether your numerical result is correct or not, because it's
Yes.
just simple calculation.
Yes, sir.
Yes. Okay, so we thank you for your presentation.
Thank you.
So we come to the next one. I'm not too sure whether Dr. Gautam Kumar Saha is here? Oh, you are?
Yes.
So you are the third presenter. Are you presenting?
Yes, I'm present.
Yes, okay. So the paper is on wave wash and its effects in ship design and ship operation. A hydrodynamic approach to determine maximum permissible speed in a particular shallow and narrow water channel. So, Dr. Gautam, you can start your presentation. Is Rubil Chandra Das here? Huh? Or Muhammad Riyad? Muhammad Amashud? He's not here, okay.
Good afternoon. I am Muhammad Sambin Abdullah. I'm going to present my research on wave rush, its effects in ship design and ship operation, a hydrodynamic approach to determine maximum permissible ship speed in shallow and narrow waterway. I conducted this research with my supervisor, Dr. Gautam Kumar Saha, and with my classmates, Muhammad Ashraful Jaman. I welcome you all to my presentation. Here is the outline of our research. In our research, we see we will be introduced the concept of wave rush and the wave characteristics. And actually, our plan and our motivation was to determine the maximum permissible ship speed in a shallow and narrow waterway. For this reason, for this objective, we set relationships among wave parameters, and then we conducted a particular case study, and we calculated the maximum wave height for the waterway, and then from the relationships we established, we calculated the theoretical wave height, and we conducted safety simulations, we compared among the results, and finally we came to the conclusion. Yes, our motivation was to calculate the maximum permissible ship speed in a shallow and narrow waterway, and as well as to determine speed limit and speed regulation in the shallow and narrow region of a channel. What is actually wave rush? Wave rush is a hydrodynamic tool, and sometimes it's known as wake rush also. And whatever we say it, wave rush or wake rush, it is a wave phenomena which create which can explain ship generated waves and its impacts on shore and its impacts on sheltered water. What are the problems associated with wave rush? Damage to moor structure and shoreline structure, ecological threat, endangering people's life who are working near shore or who are working in the small craft near shore, and disturbance of silt and fragile water plants. Here we will see while the researchers on wave rush had been conducted previously in many parts of the world, in USA and Canada, researches on wave wash was conducted in Crystal Lake, and shoreline and damage was the outcome of that research. And in the San Joaquin River in California, research was conducted in 2005, and the outcome, the result was there had been shore erosion of 0.01 to 0.22 millimeter per boat passage. And in Europe, there has been some researches on wave wash which was conducted in Greece, Denmark, and Tallinn Bay in Estonia. And in Australia and New Zealand, wave wash research was conducted in Waikato River and Tweeds River. On which parameters wave wash actually depends on? The nature of wave wash closely dependent upon depth-based fluid number and in our dimensional parameter, which we know as F is equal to V by root over GH. And according to the depth-based fluid number, we classified 4 speed ranges. And those speed range were subcritical speed range, and transcritical, critical, and supercritical. Here is the characteristics of the subcritical and transcritical speed ranges. At the subcritical speed ranges, the depth-based fluid number is less than 0.75, which has long-crested, divergent wave, and transverse waves are present. In transcritical speed range, the divergent angle increases as well as the period of leading wave increases. And when the ship reaches its critical speed, that means when fluid number is equal to 1, the divergent wave and the transverse wave becomes perpendicular to each other, and the supercritical speed range is known, for which fluid number is depth-based fluid number is greater than 1. We will stepping into our steps. Our first step was wave wash criterion and wave height limit. We used a formula developed by Danish professor Kierkegaard in 1998, and the formula has been given in terms of wave period, and in terms of wave period, and the wave period was is related to V. There are some empirical formulas which has been developed by Kierkegaard, and all we know about the wavelength formula and the wave energy formula, which has been developed by Kelvin, Weixenwegel. Let's proceed to our step 2. Our step 2 is to calculate the theoretical wave height prediction. We had gone through many research papers, and we found some empirical formulas. The first formula was derived by Russian professor Balalin and Baikov, and in this formula he had considered the width, the length of the vessel, as well as the depth of the water body and the cross-sectional area of the ship. And the next formula had been developed by Balous, and it was given in terms of some coefficient, the depth, and the fluid number. The fluid number is here the depth plus fluid number. Let's proceed to a case study for which we have shown the interrelation between the step 1 and the step 2, and we selected a high-speed craft, and it is operated under the supervision of BIWTA and BIWTC. Here is the ship particulars and the waterway details. The channels we considered has a depth of 6 meter at an average, and average width is 265 meter, and there is 2 regions of drastic depth changes, and these have been given in the lowest part of the slide. The lowest depth was 2.71 meter, and another shallow region was had the depth of 3.92. This is our step 3. Now we will compare the predicted wave height with the wave wash criterion. here. We conducted our research from ship speed 1 to ship speed 16 knot, but here I have presented the chart and other details for ship speed 9 knot to 16 knot, and we can see that when the ship enters into transcritical stage, that means the ship enters into transcritical stage at 12 knot, and it enters into critical stage just after 14 knots. And interestingly, we can see the predicted wave height at 14 knot is 0.55, which has shown in the farthest right side of the slide, and the maximum wave height which has been determined by the empirical formula shown in the step 2 was 0.64, and interestingly we have found that the fruit number is 0.94. And when the ships just after 14 knot, the ship reaches its critical speed, that is between 14 knot and 15 knot, and we can see that when the ship reaches its transcritical speed, the highest limit of the Wake-West criterion has been exceeded by the maximum wave height, which has been calculated using Balalian and Baker's method. And we also implemented these relationships and formula into shallow region. These shallow regions are Katasur and Gaptoli, which has respectively water depth of 3.92 meter and 2.71 meter. And here we can see that according to the comparison of predicted wave height and theoretical and Wake-West criterion, we are seeing that at 10 knot, when the ship enters into its, at 12 knot the ship enters into its critical speed, and at 10 knot the predicted wave height exceeds the Wake-West criterion, which has been denoted by HH. And at another shallow region, which has water depth of 2.71 meter, the ship enters into its critical speed at 10 knot, and but the predicted wave height exceeds the Wake-West criterion at 9 knot. From here, we can tell that the critical speed at Katasur that is 11 knot, and critical speed at Gaptal is close to 4.9 knot, where the critical speed through the waterway is 14 knot. What does it mean? It means if the ship continue to move it forward with its average speed of 30 knot or 14 knot, there will be a possibility of wave rush on the shore, and other threats can be arised at Katasur and Gaptoli. So the speed restriction must be implemented here. Let's proceed to step 4. We had conducted some safety simulation in potential flow solver, and it is the contour of the ship wave shown at 8 knots. And it is in subcritical speed. It is in subcritical speed range, and at 12 knot, it is in transcritical speed range. We are seeing again. I'm going back. Here is the divergent angle is less. The divergent angle is increasing with the ship speed, and at the 14 knot, it is increasing further. Now we are going to compare our safety results with our theoretically predicted height. Yes, here is a comparison. The table shows the simulated wave height and the wave height calculated by Bellow's method, and we are seeing there is a close harmony. For simulation result, the ship speed, the wave height increases from 0.7 to 0.9, then 1.2, and then 1.3, and according to the Bellow's method, the wave height increases 0.7, 0.9, and 0.2, 1.2, and 1.5. And the graph has been given in the next. So we can approximate that our safety simulation and our calculations are close. Here are some recommendations, and what is our recommendations? Our recommendations is to limit the highest operating speed less than 14 knots, and to exceed the if the ship speed 10 to 12, 9 to 10 knots at the shallow region, there can be a possibility of wave rush. So in those regions, some signs should be given, and the operators should be careful about this. And another recommendation is that while designing a ship and while designing the design speed for a ship in a particular narrow and shallow waterway, we should consider the effect of wave rush, and we can follow this model. And what are the further developments? The further validation by full-scale experiments and further computerized method can be adopted, and similar studies can be carried out in the important inland waterways more holistically to determine the maximum permissible speed in each important rivers and waterway. And here's the overview of our model. Our objective was to determine a critical speed, and then for this reason we used we set a wave rush criterion which had provided the highest limit, and then we calculated the predicted wave height by Valalian's method and Baker's method. We conducted safety simulations, we compared all these results, and finally we came to a conclusion to determine the maximum permissible ship speed in a shallow and narrow waterway. Here are the references from which we took the information and formulas. And I want to acknowledge Bangladesh Inland Water Transport Authority and Bangladesh Inland Water Transport Corporation, and some of our faculty members and some of my friends who assisted me in conducting my research. Thank you all.
Any question? Yeah, okay.
Can you go to the slide where you make the comparison between the wave height and the speed? I want to. Yeah, this one. So from here, from this graph, we can see that the increase of the speed, the difference between the experimental and your results is also increasing.
Yes, sir.
Why? Do you have any idea why?
Actually, sir, in the Balus method, the ship speed. Actually, the main problem is that we used a potential force solver, which has some limitations. That is why the difference is increasing with the increase of ship speed. And the Balus method, was derived in 1984, and it was derived for a particular waterway. It can be the possible reason for which the difference between the simulated result and the approximation by Balus method is increasing with the ship speed.
I actually don't think so, because potential flow method doesn't have any limitation. It only has the limitation, it doesn't consider the viscosity effect.
Yes.
So as far as I understand, if you consider the viscosity effects, I mean, if you use the Reynolds method, I think this difference will decrease.
Yes, sir.
That is my understanding.
Yes, sir.
Okay.
Okay. Maybe you can do a field measurement test to really confirm.
Yes, sir.
You can use the CFD method, then you can see, I mean, the rank solver, you can see, I am believing that the will increase.
Thank you, sir. So actually, I tried with another software that is known as Shift Flow, but we. Yes, sir. But sir, but I couldn't.
Has three, as far as I know, just I take 1 second. The shift flow in our laboratory, in our university, okay, it has a problem when it simulates the rank solver. Okay, so that's why all the researchers who showed their result in this session, everybody has a problem like this.
Yes, sir.
They call it sheet flow, but as far as I know, it doesn't consider the rags solver anymore. That is why the difference is high.
Yes, sir.
Probably there is a more potential flow.
Because sheet flow, it is a combination of potential
potential.
flow, because they divide the geometry or the section in 3 zones. Each zone they uses boundary layer, this zone they uses potential flow, this zone they uses rag solver. So the sheet flow in our university, the rag solver doesn't work. So
Yes.
actually we can consider the rag solver. That is why the difference is high.
Yes,
Not
sir.
only for you, but the previous researchers, they all have the same problem everywhere.
Yes.
You should notice this one.
Yes, sir.
Anyway, thank you.
Thank you, sir.
Okay,
Thank you.
very much.
Thank you all.
Next paper is by Rubel Chandra Das. It's not here. Huh? Paper 157. Anybody? No. Okay, so we go to the next one. Paper 168. Muhammad Azlan Musa. Yes. Oh, his co-authors. So,
Some coffee.
oh, okay, it's okay. Yeah, okay, thanks. The paper is on numerical simulation of wave flow over the overtopping breakwater for energy conversion. In short, it's called OBREC. Okay. You just can cross it. Okay. Okay.
Hello. A very good evening to lecturers, professionals and beloved people. My name is Kumar Subramaniam. I'm representing University Malaysia Terengganu from Malaysia. So greetings from University Malaysia Terengganu. To acknowledge Mr. Azlan, he couldn't attend the conference as he got some personal issues, so that I'm going to represent his paper. If any inquiries or questions, you may email to the corresponding author. So, first of all, I would like to thank to the organizer to give a precious chance to present a well-nailed topic on numerical simulation of wave flow over the overtopping breakwater for energy conversion, which is called as OBREC device. So, the introduction. OBREC device is a breakwater. So construction along the coastal areas is one of the major problem which leads to the erosion of the coastal. So it can be prevented by the breakwater. But if you want to breakwater, we need a lot of cost. So to get a long profitability, previously people invented a device called wave overtopping device, VEC. So nowadays, due to the lack of the efficiency and high cost, the invention extended to identify the OBREC device. So to get a long profitability, we combine WEC and OBREC to get a high efficiency. So this kind of study, according to the base for the erosion, we choose CFD, Computational Fluid Dynamics software, to get a good result for this device, because computational flow 3D is precisely built for the coastal affecting problems. This is the problem summary. This is the erosion along the coastal areas. So to overcome the erosion should build breakwaters, but it needs a lot of cost. So at the same time, they also need wave energy demand. This graph shows wave energy potential is unstable, so that they identifying the object under the hybrid concept, which is competitively act as the renewable energy. So the current device called object is currently in experiment. They are not applying in the reality, but still they are doing some experiment to get the best efficiency to protect the nature. There is still limited knowledge on the investigating of using CFD flow 3D technology, as a cheaper approach is analyzing wave overtopping on the object structure. This is the objective of this study. The first objective is to quantify overtopping discharge of wave with different ramps crest freeboard using CFD, which is the CFDs or based from the RANS, which is stimulation for the turbulence, and VOF, volume of fluid for free surface components. The second objective is to compare the performance of the numerical model against the current physical model of the object device. This is the current design for object. So this is the design for the object with the dimensions. So it identified that the device essentially is an integration between a traditional rubber mount breakwater and a reservoir, which acting as a energy storage by using low-headed turbines. So once the wave hit the ramp, the overtopping water will flow on the reservoir. Then the water flow through this turbine outlet. The low-headed turbine here, it extract the energy and it will store in the breakwater, and then the water flow to the reservoir. This is the current study using CFD for analyzing overtopping wave. So a lot of researches are still going on, and they are using various kind of software to identify the performance of the object device. This study is conducting under the methodology, and there are two ways of methodology they use. First is current object device by using experiment. The another is by using simulation. So simulate current object using flow 3D. So after that, CFD setup, then mesh convergence study, then finally when combine the experiment and simulation, we will doing a comparison, and then we'll get a good result for this study. This is the input data. The above table, it shows the wave air characteristic and reservoir geometrical parameter for object. And then the bottom one, it shows mesh convergence studies for parameters. It shows the fine mesh block for 1 is decreasing. At the same time, the coarse mesh block 2 is also decreasing. Here got two graph. Why not display? Yes. So there are two graphs. The first graph is volumetric efficiency against the time, and the second graph shows the mesh size is decreasing. So the first graph shows the different fine mesh sizes to investigate the most appropriate meshing to be used in further studies. So from that, we identified that 0.006 of mesh size is best significant increase of volume overtopping discharge in front reservoir when compared with the other sizes of mesh sizes. At the same time, the second graph from just now is also strengthening the above fact that shows the highest average overtopping discharge obtained within the graph is quite consistent between three mesh studies, namely 0.004 until 0.006. So this mesh study is perfectly suitable to be applied in further studies, but we should consider there are two factors. First is cost domain, which is 0.01, and another one is fine domain, which is 0.005 of the cell. This is the comparison of the current studies. So the red dots is measuring of low slope of the water, and then the blue color is a measuring of high slope of water. And then the blue dots here is the simulation of the low slope of the water, and then the yellow color, it also shows the simulation of the high water slope. Then this is the comparison to current prediction of outbreak model. So it is also shows here the low water slope is the best result in this graph. This is the snapshot picture. It shows the comparing the both graphs just now. This is the picture of this graph comparing to current experimental model. So these two pictures showing the strong negative correlation, which means once the wave hit the ramp, it will flow here. It means the excess water, the overtopping water will flow here, and it will flow to the reservoir, and the extracting energy it will store in the breakwater. So when comparing between different design formula, physical experiment and numerical simulation result, which we combine the both graphs just now, and it shows the best result is simulation of low water slope is the best result for this study. So conclusion, CFD simulation show a similar trend when compared with the experimental and formula based on quantitative observation on the graph. Even though this outbreak is not we are applying in reality, but some improvement we should imply on the device, because to get a best efficiency in the future, such as number of the wave employed, porosity upon the existence of the breakwater, and surface roughness used on the mold. So even though there are some inquiries still in the researches, but for this study, the overtopping discharge of the outbreak has given an adequate outcomes. That's the end of my presentation. Thank you all.
So we open for question. Or just maybe he will pass it to the corresponding author. Any question? So you use 3D flow, is it? 3D. Okay, do the experiment. So what is next? Eventually you have to use it as a renewable energy device, right? How good it is, the flow, everything. Is it feasible, or can it generate enough energy? Okay. So at the moment just study on the flow of this, what do you call it, overtopping, eh?
For me, it's based on the location of the
Oh.
wave. The wave speed is low, means low energy we can extract. High means the overtopping water drop on the reservoir, then high energy can be extracted from the
Okay. If there's no question, then thank you for your presentation. So the next paper is by Atul Rahman, paper 208. Marine propeller design method based on lifting line theory and lifting surface correction factors. This morning we have vortex method. Now is the lifting theory.
Transportation across the Transportation across the ocean started from the beginning of the human history. Sorry. Transportation across the ocean started from the dawn of the human history, and ship started thousands of years ago with the ship log, and now
developed as the huge complicated vessels. And the development of steam engine in the 18th century operated from the opened the windows for the self-propulsion. And the first widely used mechanical device was paddle wheel, but due to several drawbacks, it is now gradually transformed into screw propeller. And there were lots of theories to define the characteristics of the screw propeller, but the circulation theory or the vortex theory provides a more satisfactory explanation of the hydrodynamics of the propeller action than the other theories. And the development of circulation theory actually based on considering the propeller blades as lifting surface than the lifting lines. Distinguished ladies and gentlemen, good afternoon and assalamu alaikum. Welcome to my presentation, Marine Propeller Design Method based on lifting line theory and lifting surface correction factors. I am Ataur Rahman, the senior surveyor of DNVGL, and with the help of my two senior professors, Dr. Muhammad Rafaitullah and Dr. Muhammad Masud Karim. Here are the overview, first introduction, and then design method, theoretical backgrounds, applications, result and discussions, and then finally conclusions. Here is our objective. We just, by solution of, at first we will find out the solution of the lifting line theory, and then solution of the lifting surface theory for these corrections, for the results of the lifting line theory. And then we will consider also the viscous effect also to get the more accurate results with the practical problems. Now here is a flow chart for our design method. We have some known data, thrust, diameter, number of blades, and then shaft revolution, ship speed, and the wake. And then with this lifting line, with this data we just calculate, we can advance ratio, thrust loading coefficient, ideal thrust loading coefficients, and from the Kramer diagram we can find the ideal efficiency. And then from the ideal efficiency we can find out hydrodynamic pitch angle, and then the optimum one by trial and error method. And then from the lifting line theory, we can calculate the thrust, torque, and the thrust coefficient, power coefficient, delivered power, and some design sections, some characteristics for the design sections, this lift coefficient, this chord camber distribution, and then power distribution. And then from the lifting line surface correction, we will solve the lifting surface equations to find the correction, and then finally we will find the corrections. Here the theoretical background actually comes from the, as it is stated in our topic also, it is lifting line theory and the lifting surface theory. So actually lifting line theory is the propeller blade will be replaced by some radial vortex lines, and the free vortex sheet extends downstream for each lifting line performing an approximal helical surface. Propeller is assumed rotating with the angular velocity with these angular steams. Actually there are some limitations also. Due to low aspect ratio of marine propeller blades, the lifting line theory is sometimes giving you unacceptably large errors, and that's why we need to take some corrections from the lifting surface equations. For reducing this induced velocity from the lifting line theory, we used here the Biot-Savart law. In generally, Biot-Savart law is generally well known for this calculation of electricity or this induced electricity. But here we also introduce here for this Biot-Savart law to find a induced velocity on a vortex line. And then here is the normal on the helical surface. On the helical surface, we will find the equations for this induced velocity. And here is the circulation. And then lifting surface theory actually is basically determine the camber and pitch angle at different radius of the propeller. And these camber lines of the propeller sections are calculated from the lifting surface equations using blade contour and the loading distribution. The radial load distribution and the hydrodynamic pitch angle from lifting line program were taken as input of the hydrodynamic, for this lifting surface. Actually, lifting line outputs will be considered as input for the lifting surface theory. And pitch and camber corrections were required. As now this comes to our assumptions. The blade outlines assume symmetrical, and the section thickness is symmetrical at the midchord, so there will be no pitch corrections. So only the camber corrections is required, and the camber corrections will be noted as K. So here are some basic assumptions. The fluid is frictionless. Then the two important one is at the bottom actually. The bound circulation is 0 at the blade tip and at the hub. So that is our main assumption. And another one is the camber is parabolic profile. Actually, this camber parabolic profile we use to make it suitable for the high-speed craft, because our reference data was for high-speed craft, so that's why we take the parabolic shape camber. So here is the theoretical background of this lifting surface theory, and here is the reference data. The reference data is US Navy combat ship. That is here is the basic data. We collected it from one paper. We will show you the reference of that paper afterwards. And these are the basic parameters, and that was our actually previous input. We take it from the US Navy combat ship, and that is the data actually we received after using the lifting line theory. And after getting this lifting line theory, we also check the cavitation, because it is an important phenomena. So we also check the cavitation, and we found it is a non-cavitating. And then we just show you how it will be corrected. As we told you before, that as it is a symmetrical shape, so no correction required for piece diameter ratio, but for the camber chord ratio, we have to correct it by this correction factor K. And here is our some data of calculation, what we have done to make this paper. And this correction factor K is calculated on some chord ratios, 0.45, 0.65, and 0.85. And then here is the corrected data. Then first it is uncorrected data, and then we find out the K for this. We already show you for 3 sections. For 3 sections we calculate the chord, the correction factor, and then we calculate it for all the sections by interpolation and extrapolation. And then here is some result. We can show you this radial distribution at different chord, and then here is chord-wise this circulation distribution at different points at 0.45, and then sorry, I think some data are missing, so it's okay. Maybe. So it is just at the we try to find out, show you the the validation of our program, of our method, is it working or not, and we find that from our reference data, our value is and from our program, the two data's difference is only 0.19%. So that means our program is very similar to give the approximate result to the original one. And also validation check this circulation from the lifting line theory. We find the lifting line theory, and then by integration we can find it for the lifting surface also. And here is, you can see the difference is also very less, which is less than 1%. So difference. And then again also validation also, we can comparison this radial variation of this hydrodynamic pitch also, and at the footnote there is our reference value from where we get, and the blue one is our present work. So also here is comparison of this circulation, and comparison of pitch diameter ratio, and comparison of camber distribution. And here is some differences you can see at the end and at the beginning. So actually that is for our assumptions, because we assume that the bound vortex at the hub and at the tailing edge is 0. That was our consideration. So that's why you find some variations at the hub and at the tip actually. So that's why there are some variations. And here is one actually we want to show, that is the iteration, the trial and error method what we made for to find this CT value from the ideal efficiency. From the Kramer diagram we find this ideal efficiency is 0.77. So that's why we started, once we started from the 0.77 to find the value CT, and then we just try to make it more easier, that if we can or what can we do, we have no Kramer's diagram, so how can we start? That's why we start for another value 0.7. Let's take 0.7, and then from the both efficiency we find the same CT value. So that means that it is also the same. And then another validation of our program, we just try to increase the thrust to and also decrease the thrust 10%. So that because as it is our method, so that's why we want to show that if the design thrust is increased 10% or decreased 10%, then the result have the same pattern. Results have the same pattern, and this is for pitch diameter ratio, and this is for camber chord ratio. And also it is also the same, that at the beginning and at the end it is different because of our assumptions. So conclusion, actually this is this method we can find the propeller for propeller characteristics for the advanced stage by lifting line theory, and also with some lifting surface corrections. And here the results from the reference data and our method, which is very much less than 1% of the initial data, and we adopted the wake, so that gives the more accurate results. And here are the references what we made. And thank you very much for your kind attention. Here I conclude my presentation. Thank you very much for your kind attention.
Question from the floor? Very quiet. You're sleepy, eh? So just now people are going using CFD, you know. How is your computation method as compared to CFD?
It is just analytical method. It is just from the theoretical from the aspect. We did not consider the CFD method now. Maybe the program may be extended to the CFD for some further use or some further.
Because your advantage, your methods, it doesn't take long. CFD takes longer time for the computation, but it considers the viscous effect. But I'm not too sure. Propeller has a lot. Any portion, a lot of viscous effect in propeller thrust. You think? Because you are using more the vortex, right? Using the vortex.
Yes.
How about viscosity? Is there a lot of viscosity? Because the propeller is very short,
Yes.
so there must be some flow problem, laminar or something like that.
Yeah, we use.
Because your computation won't have any boundary layer, isn't it? No boundary layer will be considered. Boundary layer, separation or something like that.
No, boundary layer is not considered
yes.
here. Yeah.
Okay, maybe that's, if you can compare, then you can see how many percent difference. Yeah. Anyway, thank you very much for your presentation.
Okay, thank you.
So the next paper is by Mahmudur Rahman. Okay. Titled Dynamic Response of a Floating Coupled Spar Platform in Deep Water.
Assalamu alaikum. Good evening. At the beginning, I would like to acknowledge the first author, Mahmudur Rahman Shoaib, who is the correspondent author, and I'm Najmul Huda, just here to present the paper. If you have any question or any queries, you can contact with the corresponding author, Mahmudur Rahman Shoaib. So, the title of the paper is the hydrodynamic responses of floating coupled spar in deep sea. So, and this paper came from the University of Malaya, Kuala Lumpur, Malaysia. And let's start with the introduction. The oil and gas are the most widely used form of energy that the world has ever known. And this energy has increasingly demand for the hydrocarbons. Oil and gas exploration in deep and ultra deep water has become great challenge and concern in all over the world. And several deep water structures have been installed worldwide. However, new oil and gas fields are being discovered in the deep ocean. Then spar platform is new generation offshore structure for functioning oil and gas exploration, storage and offloading in deep and ultra deep ocean. So now comes to the components of the spar platform. So this consists of hull and station keeping system like mooring system, anchors, etc., and the riser which will extract the oil and gas from the seabed, and the superstructure is at the above of the platform. So why spar platform is needed? Because we have some advantages, like the center of buoyancy is always above the center of gravity, that's why it's always stable, and it can operate till the 3000 meter water depth, which is the huge, and take the huge payloads at the top side, and can be used as mobile drilling rig, and the mobilization cost is very low, and the economical due to less structural weight, and the structure is simple, and many oil companies are considering it is as the next generation of deep water offshore structure. And you can see the picture here, how it's operated. There is a hull and the mooring line, and at the top there is a superstructure. And the objective of this paper is to study a fully coupled spar platform subjected to wave force under regular wave loading. Actually, at the present stage, either hull or mooring line is analyzed separately. In these studies, we are trying to combine this hull and mooring line at the same time. That's why we are calling it fully coupled spar platform. And this coupled spar mooring integrated system can be used to perform damping effects, analysis of mooring lines, and to obtain the coupled responses. And this is the fully coupled analysis, which I was saying that the hull and mooring is analyzed at the same time to take the responses simultaneously under the wave forces and the other forces. And the next, the research methodology. In this study, we use the Abacus and Aqua software to analyze the spar hull and the mooring line at the same time. And this is the spar hull. Spar hull is modeled in Abacus as a rigid beam, which will be anchored with the mooring line to the seabed. Mooring line is modeled as a such that it can they can improve all types of significant nonlinearities, and seabed modeled as that mooring line will not penetrate the seabed, it will be at the seabed only. And here is the nonlinearities, the geometric nonlinearities. These will come from the large deformation in the mooring line and the pretension. And the boundary nonlinearity, it will come from the contact of the mooring line and the seabed. And the force nonlinearity, it will come from the variable submergence and the added mass and the damping. And these are the geometric data for the model. The spar was length 213 meter, and diameter is the 40.5 meter, and draft is the 198 meter, and the mass. All these are modeled in the Abacus, as you think. And here is the mathematical formulation which was considered for analyzing the nonlinearity, and this the M for the masses, and it comes from the structural component and the added mass at the top side of the hull, and C is the damping. It will come from the structural damping and also from the hydrodynamic damping, and the K is the elastic constant and the geometric constant. So, however, from this formulation we will get the Ft, I mean the force which will act to the mooring line and to the spar hull. So, and we also analyze the response amplitude operator, which is rho, to show the behavior of the platform with the 6 degrees of freedoms. And this is how the software analyze to achieve the stable configuration. The step 1, the equilibrium under inline tension, and then at the second step, the lower the anchor point to the seabed, and then the move the anchor point to obtain the required pretension, sorry. And 4, the stable configuration. In this condition, the spar hull will be stable. And all this data was used in the model is the scale up with the experimental model from experimental model. So that's why we can also validate the data with the experimental model. However, in this discussion, we will not show any validation, but this experimental model was scaled up for our model actually. In the resultant discussion, the coupled dynamic analysis in time domain have been performed under regular wave and hydrodynamic loading. The C state is critical, where the wave height is 11 0.15 meter, and the wave period is 10.696. All those things will come at the resultant discussion section as well. So this is the resultant discussion. The surge motion of spar at platform level. So you can see that surge at the regular wave condition. So at the peak of the surge response is the 14.90 meter to at the negative point, the 10.11 meter. So it is the predominantly periodic, and it becomes stable after after 5,000 cycle. And the heave motion of the spar at the platform level. Here is also the heave response maximum peak touches to the 0.52 meter in case of wave loading for severe sea environmental and the downward translation of the spar hull stresses to the negative crest, the 0.54. That means it's in between the 0.52 to minus 0.54. The mooring tension and the other operations are influenced by the spar hull heave responses. And the pitch motion of the spar at the platform level is also the history output of the pitch responses show regular fluctuations initiating for 0 up to the peak of plus minus 0.07 radian. And the significant value of the pitch response leads to the momentous surge at the deck level, and responses are regular in fashion, and effect of the nonlinearity alters the pitch motion responses. And the top tension in the mooring line. Mooring line shows the regular behavior of tension under severe sea environment. The design pretension in each mooring line is the 1.625 into 10 to the power 7 Newton, and the maximum value obtained the 1.72. And the fluctuation of time series remind the precise consideration are required for stable structure. And here raw values for the sieve arch pitch, heave pitch, and the mooring tension also. For the four stars, heave and pitch, and the mooring tension. However, the conclusions are the deep water spar model maintains the structural continuity and capture the coupling of platform mooring plus seabed mooring interaction along all the possibilities nonlinearities in consistent manner, and it is expected to greatly promote operation in deep sea exploration. The simplified couple analysis approach for spar platform incorporates computational and saving to predict responses, maintaining acceptable accuracy rather than the complex experimental study. And rigid body resonant motion influence the dynamic motion responses of spar, and the responses are periodic in nature. High degree of nonlinearity involved causes irregular response characteristics of mooring lines and wave frequency levels. The response in surge, heave, and pitch considerably decreases for long duration of wave loading, though top tension in mooring line reduces as well. Because of high pretension, quite regular values are seen at long duration of wave loading. And thank you very much.
Thank you very much. So you are ready for a question now? Okay.
Because
Okay.
I'm just a presenter here.
Okay, if anybody has a question, just you can,
I can pass to
it to the corresponding author. Yes. Yeah, okay.
I just wanted to know three things. One is the environmental conditions.
Yes.
So is it like only, do you only consider the wave flows?
These are the wave.
Only wave flows?
Wave.
So it is nothing wind or current, nothing?
No. These are the wave loads.
And the maximum tension you say, you had a pre-tension.
Yes.
And you say the maximum tension, which is, pre-tension was 1.6 and 20.7.
Yeah.
And the maximum was 1.7.
Unfit.
So is it the maximum load from pre-tension plus, that is 1.6 plus 1.7, or the different, I mean, you understand it?
Yeah,
We
I
had
understand.
pre-tension 1.6.
Yeah.
And the maximum was 1.7.
Yeah.
So should I consider that maximum was absolutely 1.7 or 1.6 E7 plus 1.7 E7?
Actually 1.6 plus 1.7.
Okay. So we thank you for the presentation.
Thank you very much.
The next paper is by Professor Sadiko Bari on seakeeping performance of Series 60 ships.
We are asked to design different types of ships. And while designing, usually plans of the body plan of the vessel is not usually available. And it is one of the requirement that we should design a ship on the basis of on a sea route where the vessel is expected to ply. And usually certain percentage sea margin is considered for prediction of engine power or determination of engine power. And usually the practicing naval architects don't have software to go into investigation or detailed computation in general. So, in order to help the naval architects for a quick determination, reasonable determination of how much extra power or extra resistance a ship is going to experience in a seaway at different sea states for different wave headings, that is a requirement, and on that basis, previously a work was done by Lukakis and Chrysostomidis. He presented a seakeeping standard series for cruiser stern ships, and it covered a wider range of responses. But that was a lacking that the sea states which are considered were very large for long ships, and usually those that very long significant wave height, very high significant wave height, is usually not experienced by smaller ships, usually. And secondly, another researcher, Grigoropoulos, he published another seakeeping tables for Series 60 ships, considering oblique waves, oblique seas.
The first one, Chrysostomidis, he only presented the sea-keeping results in terms of head siege only. But later on, Grigoropoulos, he presented sea-keeping tables for the same series of ships in oblique siege. But in both the papers, added resistance due to wave reflection has not been considered. Again, in irregular, there are very limited or very inadequate results in oblique siege. So, it was my intention to re-evaluate the sea-keeping performance of Series 60 ships, considering both head and oblique siege. So that is the objective, to re-evaluate the sea-keeping performance of Series 60 ships. Parent form, I have considered here only parent form for head and oblique siege in terms of added resistance, because added resistance is a major sea-keeping parameter. So in terms of added resistance, I will try to present, have tried to present the sea-keeping tables. For this purpose, the theoretical procedure which I had to follow, as you know all, that the first primary step is to determine the ship motion, and which was performed by ordinary strip method. Then on the basis of ship motion results, Mario's method was applied for prediction of added resistance due to motion in regular waves. Then Fuji's and Takahashi's method was applied for prediction of added resistance due to wave reflection. Total added resistance was obtained by adding the added resistance due to ship motion to that due to wave reflection by Fuji Takahashi's method. And these were done in regular waves or regular siege. In order to predict the performance or the values in irregular siege, as you know that we need response samples to operators and wave spectrum. Here, 2-parameter wave spectrum formulation recommended by International Ship Structure Congress has been applied. So in this way, the total added resistance in sea wage due to head and oblique siege have been determined in terms of ship parameters. And the results of 5 Series 60 ships parent form in terms of added resistance has been presented in tabular form as function of ship particulars, fluid number, wave heading, etc. And the non-dimensional parameter which has been used is this. The mean added resistance into 10 to the power 10 divided by rho g LB to the LBP to the power cube, and then significant wave height square. Calculations have been carried out at 2 different beam draft ratios, one for 2.5, another is 3, for a range of 8 modal periods with non-dimensional values of 1.5 to 5 at an interval of 0.5 intervals. And the modal period have been non-dimensionalized by this TP divided by square root of LBP by G, where TP is the modal period and this is the non-dimensional value. So on that basis, I have presented here, I have included here 2 tables, one with a block coefficient of 0.6, L by B ratio 7, B by T 3. This is the heading angle, this is the modal period, these are the fluid numbers at 5 different fluid numbers starting from 0.1 to 0.3. I have carried out computations. Here presented at 2 different fluid numbers, the tables. These are the modal, non-dimensional modal period. These are the wave headings 180 on 50, starting from 180 to 0. These are the values. This is for block coefficient 0.6 at a beam draft ratio of 3. Then another table is for series 60 ship, block coefficient 0.7, same beam draft ratio, and at two fluid numbers, 0.15 and 0.25. Here is a comparison. I have showed the comparison with Grigoropoulos, who presented his seakeeping tables. This is a significant wave height by LBP, it has been non-dimensioned. This is percentage added resistance in terms of calm water resistance. This one is the present method, result for the present method, and this one due to Grigoropoulos. This is for heading 180, this is for 150, this is for 120. As you can see that over here the comparison is very close to each other. As you moving towards head C, bow C and head C, the margins, the differences increases. The reason is that which I consider, Grigoropoulos, he considered a different strip theory for prediction of ship motion, Solvenson-Tux, and he applied Geretsman's method for determination of added resistance due to motion. On the other hand, the present method uses OSM for prediction of ship motion and Monroe's method for prediction of added resistance due to motion. In addition, it also includes Fuji Takahashi's method for prediction of added resistance due to wave reflection. Again, the differences may be due to this, that Grigoropoulos, he applied Brest-Neither spectrum formulation for prediction in irregular C, whereas here ISSC, two-parameter spectrum, has been applied. So these are the reasons why there is a discrepancy. I don't want to say discrepancy, the differences between the two results, what may be the reasons. And I would like to draw the attention that these figures are only for modal period of a value of modal period Tp prime is equal to 4. So this is the work, and these tables are very important. These are tables. There are 10 tables, in fact, in the paper. I have shown here only 2 tables. These are important in the sense that a naval architect, while designing or predicting performance, especially of this type of ships, he can use these tables for initial determination of how much extra resistance a ship is going to encounter. And from there, he can determine the power requirement of his main engine. So, although the present work does not include a wide variety of ship responses, but the parameter of added resistance is nevertheless a very major factor in the prediction of ship performance in a seaway. And on that basis, moreover, this is one advantage, that it includes all directions of waves, which a designer will need for determining the performance of a ship in a particular route, and can assess the margin, how much a ship power will be required in a seaway for a particular route. So with these things, I would like to conclude that it doesn't cover plenty or wider responses, sea-keeping responses, but the major parameter, the major sea-keeping parameter is included in different tables for the Series 60 parent form ships. So with that, I conclude my presentation. If you have any questions, you can ask me.
Questions? On seakeeping? Designer, ship designer? But naval architects seldom use the table for seakeeping. Number one, just resistant propulsion, because it's in the contract to achieve the design. If there's any naval architect want to comment on. In maneuvering, there is a resolution from IMO or turning circles, but seakeeping there's no resolution. Yes, but it's more for this. I think maybe with EADI, maybe it become more important because of this requirement to reduce emission. Yes, but it will be a problem. If ship goes too slow, then it doesn't go forward with the waves. Yes.
There's no risk in inefficient first question is your method, is it a software output or just simple business?
No, it's a program. It's not software. It's a there is a coding. There is a program. On the basis of these theories, the program was developed, and it is available in my department with me and who are working in this field. Computation on the basis of the program.
So nothing empirical.
Nothing empirical. It's not empirical. On the basis of those theories, Marlowe theory for radial resistance, motion theory, OSM for motion prediction, for wave reflection, all these have been predicted and have then applied the ISS spectrum, combination of irregularities. These are all programs. On the basis of those theories, not a commercial software. Three wave reactions. RNT 151.
And for all those curves, the methods which you use, I think they give much more energy resistance than the usual one.
Right.
So do you think is it because of the lack of clarifying the other terms, which I mean you are trying, I mean you have a method and the other method. The other method, if they miss something which resulted in a lower resistance or
Yeah, very good question. I've said the differences may be due to many factors. One thing that the results which are compared with reference to, it's very difficult to pronounce the name Grigorov-Boulos. Anyway, he applied Paulding's Salvesen-Dux method for ship motion. Then Geddes-Mars and Buchelman's method for ship adhered resistance. And then Wills-Snyder spectrum for prediction in irregular seas. 3. But in my approach, I've used OSM for ship motion, Marlow's method for adhered resistance, and Fujitaka's method for wave reflection, and ISSC, International Structure Congress, for wave spectrum. So his approach is the same, but the methodologies or the theories he is using and we are using is different. So I want to say that because of the different theories used by him and us, the results are different. And how much different? If you go towards 120 degrees, then the difference difference is very close, very near. There is almost coincide. But as we move towards head seas, 150 and 180, the differences is more. The reason I point out that in their method they have not considered the added resistance due to wave reflection, whereas in our method it has been considered. These are the reasons why there is a difference, because of those things.
Okay, so we move on. Then thank you very much, Prof. We'll give a round of applause. So the next paper, our second last paper, is by Akbar, Hashemi Akbar, Outrigger RC boat hull model development as a high-speed craft based on resistance and lift force. Oh, yeah, okay. You're late. Okay, you come after him. Huh? So we have 2 more papers, and we should finish by 4:30. So I hope you can stay until 4:30. Yeah?
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Om Swastiastu. My student from Hindu. Okay. Thank you. My name is Bagio Swasono because my student is accident. Jadi I can change to present it this paper. And my institution developed RC boot model. This type of trigger, and my student Trimaran, we give to in front, we give call all trigger, and behind Trimaran. Introduction maybe multi hull, because I develop step by step to give to Bernoulli approach. I give step by step and to my student and for me and for us and my institution. The design RC boot or trigger, we give 3 models, and baseline model E, and B and C. We get comparison 3 models. We try to build 98.5 and 98.5 entry, and different is model C. Model C SOA-nya 9.8, and bread molded is 17, and model B and model C 2020, and draft the same. I build a launch plan. I try to CFD simulation and pressure, and 3 models, model E and model C is developed for us, because develop B pressure is 4.2, and model E and model C minus. built this model E and model C. This result simulation 20 knot because I give to introduce speed planning how it minimum 25. I give built-in 20 knots. And the system and slider body, we give fruit number, speed ski, planning how. The outrigger, because outrigger first run Archimedes approach, because we high speed, fruit number, this change to Bernoulli approach. Maybe I try to develop to research again. This conclusion and my research. This is spirit and line is very difficult to me approach about 20 speed we and try last experience we can get 50 knots 50 meters per second. We can try about 26.5. Thank you. This we can try to competition or trigger competition model. One year when usually develop model, we can give competition to student. This outrigger, electric power, not engine, because color is usually is very high and very good. We can change power engine and 92 octane, number octane 92. We can give support from Komatsu, Zeno Komatsu 30 cc. The power maximum we can get 50 meters per second. This speed is very it's very difficult for me and give challenge for my student. Thank you very much and respond for me. Thank you.
So any comment or question? But we are short of time. We have 2 more papers.
We can give fcboat.hangtua.ac.id. Maybe give collaboration develop to fcboat. We can next time maybe collaborate in Malaysia. Maybe I play in Malaysia, Sarawak and Brunei Darussalam. We can get 2 catamaran. We can use engine and octane 92.
What size you have?
Yeah, catamaran, not outrigger, which developed for us. Yeah, catamaran.
Size?
Material 1 meter 25. This is developed 55.
Oh.
Step and 1 meter to 20. Standard from American standard give me 125 minimized. We go for us for me. Any question? Maybe you're interesting for my student, for us. Maybe collaboration for SC boot model.
Okay, thank you very much.
Thank you very much.
So the next paper is by Muhammad Sadul Alam Cheon. Just to announce, the closing ceremony 4:30. So can we make it a quick one? 10 minutes.
So, respected session chair, most respected faculty members and dear audience present, Assalamu alaikum and a very good afternoon. Okay, so this is my presentation on comparative study on the hydrodynamic performance of porous and non-porous submerged breakwater. This was co-authored by Afifur Rahman, who is lecturer of Department of WA, and Dr. Mohammad Atar Rahman sir, who is currently the professor and head of Department of WA BUET. Okay, so before I delve into the details of my presentation, I'd like to dissect my topic so that it gets more clearer for you to understand. So first of all, I'd like to explain what is breakwaters. So breakwaters, as you can see, these are offshore structures which protect a harbor or beach from the falls of waves. So with that red line, I have shown the breakwater which was constructed to keep a tranquil environment on the other side of that breakwater. Next comes what I mean by submerged breakwater. So submerged breakwater is when the height of the structure is less than the total still water height. So you can see that the crest of the breakwater is below the still water level. Then comes immersed breakwater. So as the name implies, the immersed breakwater is when the crest of the breakwater is above the still water level. So next comes, there was another term called porous and non-porous breakwater. So porous breakwater when the structure is not solid, that is we have slots between the structures, this one is porous breakwater. And then comes the non-porous breakwater. The image is not that much clear, but it is wholly solid, that is there is no horizontal or vertical slots between in that structure. Then this is the longitudinal experimental setup. So these are some ML by ML 1, 2, 3, these are the measuring locations, and that black boxes, those are the breakwater planks, parts of the breakwater structure, and this is how we have generated the waves in our laboratory, and at the last part we have that wave absorber. So porous breakwater which was used in that experiment, we used porous breakwater at different porosity. So by that porosity we mean the gaps between the planks. We have 40%, 50% or 60%. For that 40%, as you can see, there are different plank sizes and different gap sizes. And there was the other breakwater that also had 40 centimeter height, and that was done in the same laboratory, so same width, but this was completely solid. Okay, so this was the two-dimensional wave flume way I have used. The dimension is given below, and this is the wave generator. By the back and forth motion of that wave generator, the wave is produced in the flume. And then comes the wire screen. This is made to make the waves more uniform and unidirectional. Then comes the wave absorber. This is used basically to dampen the waves so that there is no effect of reflection on that. So I'd like to show you a part of my video now. Okay. So please wait. So I'll first forward it as the time is less. So basically this is the experimental setup from where the wave is being generated. Then as we move forward, we have this wave is being generated, and then this is our breakwater structure. As you can see, so that scale, we can actually measure the wave height. This is the position where the wave is being broken. Sometimes it happens upstream of that breakwater, or sometimes downstream. So this is how the data was taken. So as the time is short, I am skipping the video now. Okay, so going back to the presentation. We have, so this is the experimental run conditions. We have used different wave period, we have used different incident wave height and corresponding wavelength. So let me go to the result. So what happens is that we may use solid breakwater or we may use porous breakwater. The energy height is, the percentage reduction of wave energy height reduction is different. So basically this is what has been substantiated with my experiment. So as you can see, when N, the N means porosity, N equals to 0.4, we have the energy percentage reduction of 47. But when N is equal to 0, that is when there was no porosity, the structure is completely solid, the energy reduction percentage is 58%. So this is, as you know, the energy reduction, the energy of any wave depends on its water height. So basically this was calculated by calculating the wave height, the reduced wave height upstream and downstream of the structure. So we also calculated some hydrodynamic coefficients like reflection coefficient, refraction coefficient, and transmission coefficient. I would not go to the mathematical details of those equations, but so that you can understand the graph, let me just show. So wave reflection coefficient in case of n equals to 0, that is when the structure is solid, we have the maximum wave reflection coefficient. That is understandable also from the common sense, because if the whole structure is solid, of course, it will reflect the waves more vigorously, which is of course very important in case of when you design, because the scour depth depends on how much wave energy is being reflected. So this is about the case of wave reflection coefficient. Then comes the wave transmission coefficient. The higher the porosity, of course, the more water, that is the more wave energy will be passed and the less will be dissipated. So the transmission coefficient is maximum for n is equal to 0.6. And then comes the energy loss coefficient. This is also explainable, self-explanatory from the graph. So finally, I'd like to recapitulate why I'm calling it a comparative study and what has been shown here. The first 3 rows, they show the different wave height reduction percentage and different hydrodynamic coefficients for different porosities, and the last one that shows the wave height reduction and different hydrodynamic coefficients for the non-porous one, that is the solid structure. So this is all from my part. Thank you so much for your patience hearing. Thank you, sir.
So we have one last paper. Aerodynamic CFD analysis of passenger vehicle bearing inclination angle of rear end spoiler by Rule Chandra. You can make it in 10 minutes.
Good afternoon. My paper titled CFD Analysis of Passenger Vehicle at Various Angle of Rear End Spoiler and presented by me, Rubel Chandra Das. Outlines of my presentation: introduction, design criteria, numerical method, spoiler and its benefits, result interpretation and conclusion. First of all, introduction. Automotive vehicles run so much fast, which creates unexpected accident for such excessive amount of speeds. It is observed that an automobile experiences an uplift force while traveling at higher speeds. Therefore, the automobile loses traction with the road and drivers fall into problem to control it. The shape of the vehicle uses 3% of the fuel to overcome the resistance in urban driving, but it takes 11% of fuel for the highway driving. Spoilers are such kind of external devices which are designed to reduce lift, also making considerable increase in drag. The invention of the spoiler was inevitable because having capability for reducing aerodynamic lift in the view of safety aspect, it is more important. Numerical method. CFD, I used Autodesk CFD simulation software to analyze my paper problem. It is handle fluid flow problems. First of all, 3 basic elements: pre-processor, solver setting, and post-processor. Design criteria. In figure 1, we have seen that 3D vehicle model with relevant dimensions. Figure 2, spoiler model with relevant dimensions, and here a virtual wind tunnel for simulation, velocity inlet, pressure outlet, symmetry side. It is the overview of solution procedure. First of all, initialization, then solution control, monitoring solutions, CFD calculation, then check for convergence. Here, yes or no. If it is no, then modify solution parameters or another base machine is required. If it is yes, then stop. Its spoiler here in figure. Benefits of spoiler: maintaining traction, increase fuel efficiency, added visibility, reduce weight, create a stylish look, increase braking stability. Here is about spoiler. A spoiler is fundamentally an inverted aircraft wing. The wings of a aircraft generates lift, which helps the aircraft take off. While the spoilers also generate lift, because they are inverted, they push the car down on the ground. Now there may be a question: why do we need to push the car down on the ground? Generally, at high speed, the air under the car is moving slowly, much faster over the body of car. The whole car hence starts to act as a giant wing and may take off from the ground. Yes, that is true. Also, if you want to turn the car at high speed, Newton's first law makes sure that the car has trouble turning. Well, when a car travels at high speed, it has a lot of momentum in the particular direction it is going. Now, with the spoiler in the car, it pushes the car down, generating extra weight on the tires. And it is our basic phenomena to safe driving. Now, my result interpretation. Autodesk simulation CFD software. These figures are static pressure on the cars at various inclination angle at rear end spoiler. In A, -2 degree, 4 degree, 6 degree, 8 degree. Various types of designs are made in rear end spoiler. Here, how flow is flown about in a rear end spoiler car. Here, -2 degree angle, 4 degree, 6 degree, 8 degree. Now, result analysis. First of all, modification of the model. 6 types of modification are done: -2 degree, 4 to up to 12 degree. Here, coefficient of drag and coefficient lift are calculated. Here, values are shown. We have to reduce coefficient of drag, and coefficient should be reduced because for safe driving. And now I want to move graphical representation for various velocity. When here coefficient of drag is show versus inclination angle of spoiler for various velocity. Here coefficient of lift for various inclination angle at different velocity. I used 4 types of velocity: 70 km per hour, 90, 110 and 130. Now conclude my presentation. Observation can be concluded that at particular spoiler height, the spoiler possesses smaller angle of wind collision, gives higher drag force. This is due to the fact that with smaller angle of wind collision, the spoiler would create a smaller recirculation zone behind the rear end of the running vehicle. This implies to higher pressure behind spoiler, but lower pressure behind the rear end of the vehicle. Rear spoilers redirect the airflow behind the vehicle and increase the negative lift of the vehicle. In this investigation, 6 modifications are simulated. 12 degree spoiler inclination angle model is the most optimum in my simulation. It creates 1.56% extra CD, therefore 4 degree inclination angle. Minimum CL is maintained in the model, which is basic concern for better stability of high speed vehicle. Thank you. Autodesk simulation CFD. Autodesk simulation CFD. Autodesk. Yes, it has. Autodesk simulation CFD. Computational fluid dynamics software. Fluent and ANSYS, it can be used. I have used ANSYS software, and here I used Autodesk simulation CFD. For critical design, ANSYS is better.
I'm confused. Also you are talking about ANSYS and another time you are talking about
Two is totally different. If I have knowledge about ANSYS and automatic simulation CFD, and if critical design is here, then ANSYS is better, I think. My design is simple, not at all critical, so I used automatic simulation CFD, and in ANSYS, high computer is required.
Actually, then if you go your slide, I just two or three, you show the velocity vector and the velocity or something. I just want to mention two things. Go back. This one. I just want to tell you one thing. We have to be very careful when we present some CFD results, because CFD is just it gives the color picture, right? If you look at the picture, the position of the car in each slide is totally different, so it's very difficult to make the comparison. You can see the size of the car in these 6 slides is totally different. One is big, one is small, another one is like three. So usually when we present the CFD results, the shape of the body will always be the same, so that
Thank you, sir. Question. I have realized it. In visual thing, if we use fluent, then
I'm not talking about which one you are using. I'm talking about the way you represent. You show 6 figures, okay? If you show the first figure, if you compare the second figure, third figure, 4, 5, 6, the shape of the car is not the same.
Yes, sir. I have to more careful about taking figure, and my calculated result shows correct one, but I have careful about taking these figures.
Yeah, and if you go to the next slide, here you use this one is velocity vector.
Flow traces.
No. The line you are showing, this is what?
Velocity vectors.
Vector. But in aerodynamic space, most of the case we use the streamline.
Automatic simulation CFD flow traces and velocity vectors only shows.
If you show by using the streamline, okay, then it will be more appropriate.
My figure was I used this figure about my research, but in papers I used only 2 figures: static pressure distribution and
You just misunderstand my point. I say
flow.
use the
Okay, thank you, sir.
Okay, let me take you the